So Open3D, doing 3D processing besides hardware, we also need software. So Open3D is exactly for this. So let's get into that. Okay. So for the agenda today, we first are going to give an overview, introduction overview of Open3D. We're going to see how Open3D can be set up and go through the data structures that Open3D has. Then we will showcase an application actually combining Open3D with RealSense for scene reconstruction application. Then we go to feature work. We're going to discuss what will be the next exciting thing that will be available in Open3D. Okay, so Open3D is a library that's meant for general purpose 3D processing. It implements the most fundamental data types and algorithms for 3D processing, and it can be plugged into any applications you like visualization, machine learning, and others like robotics. And we want to make Open3D extremely easy and efficient to use. That's our main mission. Okay. So with that, let's roll a quick introduction video. So some of you might already seen the video in the demo. Yeah, so this shows how we clone the source of Open3D. And we have both Python and C++ API available, so you can use it very conveniently. It's also cross-platform. The next one shows the basic manipulations of data structures, such as IOs and visualization. These are point cloud processing. What we see is the normals. Oh, sorry. Okay, let's jump to that part. Yeah. The next thing we see is geometry editing. Here's the registration pipelines where we align two point clouds. We're going to go through more details of that. We also support interactive registration, which is manually picking the corresponding points. And here's some custom visualization. We can have a script that kind of loop over the scene and see, visualizing from different angles. So color map optimization is used for optimizing the color map after the geometry has been reconstructed. And finally, it's a bedroom scene reconstruction that we built for a demo. Okay. Okay, great. Yeah, to get Open3D is very easy. We are available on GitHub. We are under MIT license. We support Python and C++, as we mentioned. It's cross-platform, and we also have Conda and pip that you can download from. Open3D started as a research project at Intel Labs. This was the white paper that was published last year. And since the release of Open3D, it has gained tremendous momentum in both industry and academic. So we have now 1.5K GitHub stars, and it's still growing at a high rate. So to get started, it's pretty simple. You can just do the conventional pip and conda one-line code to get Open3D. It works in most platforms. You can also build Open3D from source by cloning the repository, cmake config, and make install Open3D. So this command works. It builds Open3D and also install the Python package inside the virtual environment. Okay. Next week we're going to go through the general architecture of Open3D. We can think of it as several layers. Right? In the very bottom layer is the foundation of everything. Right? That includes the data structures that we implement and the utility that operates on the data structures. 3D data structures as Sergey already shown us, like point cloud is an important type of 3D data structure. We have point cloud, triangle mesh, voxels, and others, right? With that, we need utilities. We need to write it into a file, read from the file. We need visualization. We need like a custom visualizer, that can be programmable. Building on top of that are the algorithms, right? We've seen in Sergey's demo, like odometry, registration, volume integration. These are all the foundation of like a full scene reconstruction pipeline. And we have all these algorithms implemented so that you can now go to the top layer, which are the applications. So as we see, we can do like scene reconstruction, we can do semantic segmentation, a lot of stuff that you can build on top of the provided algorithms and data structures. So what Open3D is trying to do is we want to build the tool that people can use to accelerate, facilitate their 3D software pipeline. Okay. So let's briefly go over the basic part, which is the 3D data structures. Right. As most of us might already know, here are the most fundamental data structures. The first one is point cloud. Point cloud is just a collection of points, right? And each point we can attach property to it, right? So each point have X, Y, Z coordinates to start with, and it can contain like color, a normal, and other properties. When we go from point cloud to triangle mesh, we're adding triangle indexes from the point cloud. For example, in this point cloud, we can say point 0, point 1, point 2 forms a triangle. So a triangle mesh is a point cloud plus the triangle indexes. On the right-hand side here is the line set. It's colored in red. Line set is a collection of edges or lines. What we see in this slide is the convex hull that contains the bunny mesh. Okay. Besides this, we also have a Voxel Grid and octree supported in Open3D. Voxel Grid, different from point cloud. A Voxel Grid is aligned in a regular pattern. It's axis aligned, and every block, every voxel cell is also spaced in a regular pattern. For octree, we can think of it as an index, a binary search version of the Voxel Grid. So we can do like efficient manipulations of voxel grids, for example, querying a point, finding nearest neighbors of a voxel efficiently in octree. Okay, so these are the 3D data structures implemented in Open3D. And to support 3D applications, we also have the image class that includes the RGB image class and the depth image class in Open3D. So we're going to see in the next section that we're going to use all these data structures and build algorithms and applications on top. Okay. Okay. Next, let's go to the applications and algorithm part. In this section, we're gonna show a pipeline, a full reconstruction pipeline, using Open3D plus RealSense camera. The camera that we use is the RealSense 415, which is the narrower, more higher precision camera. The job for the RealSense is to take RGB image and depth image, and the job of Open3D is to reconstruct the scene. So we do a toy example here, just for illustration. But Open3D has been, we have used it in larger scale scenes, as we will see in the coming videos. Okay. So, to start, all the code and documentation that we're going to describe today for the reconstruction pipeline are available online. You can go to the documentation page, or you can just get the code from GitHub page for the reconstruction. Everything is open sourced, and you can have very flexible. You can change how you want to tune parameters and change things if you like. Okay, so there are 4 main steps. First is capturing. A second one is make fragments, which is reconstruction of a local patch, a local scene patch. Right. The third one is register fragment, which means I'm gonna align two patches, merge them together. And finally is the integration of scenes. So at this stage, we can produce a mesh, right? So I think there's a question about like mesh processing. So at integration, the final output will be a mesh. Okay, let's go step by step. So first step is capturing of RGBD image. We just handheld the camera and then perform, scan the scene. The goal is to capture like the scene from different angles so that we get the full reconstruction. In the make fragments, we subdivide the scene. We subdivide the image sequence into subsequences. Right. So in this example, we subdivide them into two sequences. In sequence 0, we produce a fragment. We call it fragment 0. Right? Sequence 1, we provide fragment 1. As we can see here, the fragment 0 is missing the lower part. The fragment 1 is missing the monitor part. So since in the image subsequence we only see a subset of the scene, so the fragments only represent like a local patch of the scene. Yep. To do the reconstruction of a local patch, we need to estimate the camera poses. We need to do the odometry and integrate the multiple RGBD frames. So what we see here is the camera pose estimation. If we look at this scene, for example, the red line represents the camera center, right? And the blue box shooting out is the camera look location, look direction. In practice, we usually set, for example, we can set the coordinates as a convention of the first camera pose, right? Let's say we set it to the origin, and then odometry is performed among the frames. So we provide very flexible ways to define which frames you want to perform odometry with. By default, we have two ways. One is a frame with the next frame, like sequentially. So the first frame will perform odometry with the second frame. That means estimating the relative pose change, relative transformation between the first frame and the second frame. We also have like keyframes alignments. For example, every 5 frames, we do a odometry, right? The frame 1 will do odometry with frame 6 and then 11. And we then formalize that odometry into an optimization problem. So that that is equivalent to solving the loop closure problem. So this one is a more like general form of loop closure. So we don't actually require the camera to like go back to original location. But if we formalize the camera poses as a pose graph, we can just optimize the pose graph such that the odometry match the global pose. So that's also we can think of it as a more general form of the closure. Okay. So the next step after we make the fragments is we're going to perform a registration. Right? There are many registration methods. In the pipeline, we use like color point cloud registration, fast global registration. In fact, we use a combination of them. They are good and bad for like different reasons and suitable for different scenes. And we tried in our pipeline to make them as generic as possible. For example, in the registration pipeline, we do a multi-scale registration, which is downsampling the point cloud into voxels using different voxel sizes. So then we align those voxels, downsampled point cloud, in the corresponding size, and then combine the result together. So we aim to make this very generic and can be applied in many different scenes. Right? So the final step is that we integrate the scene. Right? At this point, we will use the TSDF volume and then run a marching cube algorithm to extract the mesh out of the integrated TSDF volume. The TSDF volume is responsible for integrating multiple RGBD frames. So we can think of TSDF as a average of the RGBD image. For example, you have an RGBD image, and then you have some value casted in the space, right? And you have another RGBD image, some other value, and then the TSDF will store those values in a grid pattern, and then we run marching cube to extract the mesh from that. Okay. So here are the two fragments combined. We can see that the scanning, the camera pose, it's connected from the first fragment to the second fragment. Right. Okay. Yeah. And then in the final scene, we see that the lower part is visible now, and also the monitor, the front of the monitor is complete. So we combine the information of the two fragments. Okay. So this is just like a summary of what we discussed. So first we do the RealSense capturing, and here's we use the camera to scan the scene. And then we run the registration pipeline, a reconstruction pipeline. The reconstruction pipeline here includes the pose graph optimization and integration, so include all the steps. And then we can have some visualization. The first one is the registration of the point cloud. Next is the camera pose visualization. Yeah, and here's the final result. Okay, great. Yeah. So now it's time to discuss the future work. So we actually have quite a few exciting new stuff that we're going to add to Open3D, and some of them is already in the beta format. So the very first thing, we want to make Open3D the 3D processing library. So we're going to continue improving, we're going to continue adding more data structures in Open3D. We're going to add more functionalities, and we're going to clean up the API such as consistent and easy for the user to use. Right? The second big one is integrating with deep learning engines. So in this, we've done experiments with using Open3D to implement a custom TensorFlow op. So a TensorFlow operation calls into Open3D to do certain operations. It can also, for example, computer gradients with Open3D. It's embedded in TensorFlow op. We've done a semantic segmentation example of that. We also have integration with PyTorch. We did it in a Jupyter Notebook demo that we will see. So, the reason why we like this direction is now the deep learning applications, a lot of them are 3D based. So being able to develop the pipeline easily and efficiently is important. So we provide integration with deep learning engines. So here comes the demo. The first one is a Jupyter integration with PyTorch. So what we're seeing here is a PointNet classification for point clouds, right? So here's the airplane, and on top we can see, okay, this is the airplane. So it's okay, it's 100% airplane. It's the prediction of the airplane. And the middle cell there is the Open3D's WebGL integration. So Open3D can be used inside a browser. Okay. Next, we're going to show the LiDAR semantic segmentation with the semantic 3D dataset. Okay. So here is the RGB point cloud, and here's the semantic segmentation. The blue represents the ground, the red represents the building, yellow is the car. Next, we can use that pre-trained model and then run inference on the Kitty dataset. Kitty is like a self-driving car dataset. We are able to achieve near real time is like more than 10 FPS with Open3D acceleration. Okay, so yeah, so these are the deep learning engines integration demos. Okay, and next we're going to the next thing we're going to highlight is the integration with Sparse Confidence. So as in 3D data, in a lot of scenarios, the 3D data are very sparse, right? As we see in the Voxel Grid, the valid data might only be inside, small a subset of locations. So it's important that sparse computation can be used, such that we don't waste computation in that way. So in the Sparse Confidence work, one of our lab members came up with this Minkowski's engine that operates on top of sparse 3D data. So the demo here we see is like sparse convolution in 2D data. So this can be extended into 3D in 3D space. So this method is one of the leading method in one of the semantic segmentation benchmark right now. Right. So with that, the next thing we want to highlight is the GPU integration. As we discussed in the previous presentation, sometimes it's nice to offload some heavy computation into an accelerator. GPU is one of those accelerators. And we have done preliminary work with the community, with our collaborators, on the GPU accelerated Open3D. So here's one of the very recent results that we see. We see significant speed improvements with GPU acceleration. For example, in RGB odometry, it's like 2 orders of magnitude faster. The reason for this is in odometry, we compute a correspondence of the pixels. It's like a pixel-wise correspondence of 2 images. So if we use CPU, even if you use OpenMP to parallelize, it's still not like, it doesn't help a lot, right? But with GPU, it's very natural. So with that, you can get like a high speed improvement. For the TSDF integration, we worked on like a GPU-based voxel hashing algorithm. So it's also like significantly improved in terms of speed. And in real-world test for a large scene, the overall pipeline can speed up like about 10 times. Yeah. So let's go see some videos of the GPU accelerated. So here are the standard registration demo. Point cloud ICP registration. And then this is the implementation of the fast global registration algorithm. And then we also have, we also have real-time integration. That's in this. Yeah. So this one is the real-time integration, and accelerated in GPU. So we don't need to wait. We don't need to do like an offline processing. We can just use the odometry result, and it will reconstruct the scene. In this mode, in the offline mode, we can do post-graph. We can do like post-estimation offline. But in real-time reconstruction, we have to rely on the odometry results. So it might be inaccurate if we move a long distance. But in the offline mode, we can do post-estimate, like post-graph optimization to get the loop closure thing. Okay. So these are the result from the GPU. So for this work, for this bedroom scene, using traditional like CPU-based Open3D, it takes 10 hours to reconstruct the whole scene. For GPU accelerated version, we bring the time down to 1.5 hours. Okay, yeah. So these works are mostly work in progress. We have a beta branch available in public for people to try, but we're working hard to bring them into the main branch of Open3D. Okay. Okay, yeah, here's a brief summary. So Open3D is a modern, efficient, and easy-to-use 3D processing library. It covers most fundamental 3D data structure and algorithms. You can build amazing applications on top of Open3D, especially with RealSense. And Open3D is growing fast. We have regular updates, we have an active community, and a lot of new features are being added. Okay, here are the team. So most of us are from the lab, and we are also very happy to have more than 30 community contributors very actively working on the project. Okay. With that, thank you. Yeah, I can take any questions.
Thank you very much for the excellent talk. One quick question related to PointNet.
Okay.
Is the point cloud produced by RealSense?
No. In that tool demo, I think the point cloud, the Jupyter one is synthetic. Is from some CAD model. The scene segmentation is from real scanning. One of them is from cars, one of them is from scanning.
Maybe your experience with doing semantic segmentation with point cloud produced by RealSense?
I actually haven't tried that. It should work in principle. Right.
Any recommendation on the type of algorithm, like a complex ULO versus PointNet?
Yeah. So there are many algorithms to do semantic segmentation. One of them, I think that's quite promising, is the one that we mentioned here, is the Sparse Confidence. Yeah, Sparse Confidence is one of the leading method in the scene segmentation area. Yeah.
I actually have two questions.
Okay.
One to follow up the previous one. So machine learning requires data sets. Is there a data set similar to ImageNet, but for point cloud, and in particular to the RealSense produced data set?
I see.
Is it available? Does it exist?
Yeah. There is some similar to ImageNet data sets. I think PointNet, their group, the group that do the PointNet, they have point cloud data sets similar to ImageNet.
RealSense.
Yeah, I don't think they are using RealSense for the data capturing, right? That tool, yeah, I'm not aware of such data set yet captured by RealSense.
Yeah. At the moment, we very much aware that this is a gap that we are working to find ways to complete.
Yeah, it requires a lot of manual labor. I imagine that it's 1 million images.
Yeah.
And second question, if I would build my own 3D scanner by using RealSense, what flow would you suggest? Should I move the camera? Should I move the object?
The one that I try is moving the camera, because I think that's, the assumption that we make here is that the object is stationary, and then we estimate a camera pose. But I guess you can also do the reverse. But the one that we implemented is...
But you said you're tracking the camera position while you're moving it. If you're moving the object, then camera is stationary.
Yeah, that should be possible. That's the reverse problem. But in most 3D reconstruction, the scene is stationary, right? For example, you need to scan a room. It's not practical to rotate a room. But right. It's more natural to do it in this way, moving the camera.
Thank you.
Yeah.
It's great talks. I was pleased to see the CUDA core integration. Are you working at all with the NVIDIA ISAC team about integrating with the robotics framework?
Not that I'm aware of. So the CUDA work we've done is through collaboration with CMU. So one of our lab members collaborate with researchers at CMU, and we're bringing that to the main branch Open3D soon. Yeah. So I mean that could be a good suggestion, to work with, collaborate with the robotic parts of NVIDIA. Yes. Okay. Any other questions? Okay. Thanks.